also a bit of, oh, okay. So yes, this is the plan of my talk. So I will start by very briefly introducing these three settings. You know most of it, so it should be very fast. And then I will talk about this duality as a universal duality. And then a little bit about the origins of this duality, its incarnation in free probability, and how we can manage to define some notion of higher genus corrections to free probability. And then how we manage to give moment free cumulant relations out of this master relation. And then a bit of ongoing work that probably is new for everyone about how this works in the context of constellations. So, okay, let's start. So I will be very fast in some parts because most of you know about it, but I still want to go through it in case there are new people or you have some questions. So, okay, in free probability, there is this notion of certain moments, and the counterpart on the free side, it's the free cumulant. And we know that we are interested in relations between these two objects, functional relations. We already saw this in the nice course of Mingo. And then in combinatorics, sometimes you can express generating series of maps at certain moments in free probability. And what we wanted to know is what is the counterpart of maps on the side of free cumulants. And that's how we introduced these fully simple maps together with Guy Tambourot. And then there is the third side that is actually less important for this talk, because I'm not using topological recursion at all to solve the problem of free probability of finding these relations, but it was still a very important inspiration for us and still very related to the workshop. So I want to mention the relations and what we know. So yeah, you saw already in the talk of Alexander Hock more or less how topological recursion works. And also you heard about it in some mini courses, the mini course by Reimer. So, okay, I will not repeat. It's just a procedure that associates to some spectral curve that contains the information about disks and cylinders, so 0, 1 and 0, 2. Some family of multi-differentials for any topology. So I will be referring to any G and N as the topology, where G has to do with some genus and N has to do with some boundaries or marked points. Okay, and the relation, so here I'm talking about these two dualities, the duality between moments and free cumulants, and the duality between maps and fully simple maps, and other that we will see later in this context. In topological recursion, what are these two sides? Okay, on one side, we have our spectral curve given by X and Y. We apply topological recursion, we get our omega GNs, and on the other side, we want another topological recursion problem, but for a spectral curve that is symplectically equivalent to the original spectral curve. And what do I mean by this? I mean that it preserves the symplectic form dx wedge dy. So, okay, one of the most typical ones in this context that we talked a lot about, and also you heard about it in Alexander's talk, is just exchanging X and Y. This is good enough, so you will get a minus sign there, but that's good enough. And then there are simpler transformations, and you can, of course, combine all of this. And actually, we realized that this master relation has to do with a family of these transformations. Okay, so let me tell you a little bit more about the general context. So yeah, we are interested, as I said, in the three facets of this duality. And this duality is realized in all the context so far by this thing that we call master relation, because we found that it's a quite universal thing. So, okay, I will tell you a little bit about the history of this problem, at least from my perspective. Probably this comes back to earlier, and then people in free probability can tell you better about those parts. But from my point of view, so we were interested in, so we knew that people in free probability wanted to know about these moment cumulant relations for higher orders, because they knew about the relation for first order, also for second order, even if it was quite difficult to find. And then for higher orders, there was no solution to this problem. And so we thought, okay, we can relate it to combinatorics by realizing some moments as maps. And what do we put here? And we invented these fully simple maps for that. So this is the first relation that we established using a measure that has to do with unitary invariant matrix models. And then we also realized in the context of unitary invariant matrix models that you can actually realize the relation between maps and fully simple maps using monotone Hurwitz numbers. So this is this other arrow over here. There were already some hints late in the past already by Gulden, Paquet, Novak, who defined weakly monotone Hurwitz numbers, and also by Collins, Mingosh, Nadi, Speicher, that there should be some relation between these Hurwitz numbers and free probability. So yeah, what happened afterwards is that we also found a combinatorial proof for this duality between maps and fully simple maps that was extending this problem in a different direction. So this first proof was using any unitary invariant measure. And here it was extending to other combinatorial objects. And also it gave a combinatorial interpretation of the proof. Then it wasn't until, so we also conjectured that there is this relation, and we established it for 0, 1, and 0, 2. And we also conjectured this relation to free probability. But it wasn't until 2021, so last year, that we managed to prove this. And we actually proved it together with Gaëtan Bourreau and Séverin Charbonnier, using combinatorics of something that we call ciliated maps. This I will not talk at all about in this talk, but this is how we solved the problem, by using some combinatorics of more complicated maps. And this other team of people, Bitskov, Dunin, Barkovsky, Kazari, and Shadin, they also had a proof of this conjecture last year, and they were using very strongly this combinatorial proof that we gave here. And this is actually the origin of the master relation. So what I will be talking more about today, so this arrow allowed us, of course, to establish the other arrows properly. But what I will be talking more about today is how this master relation through monotone Hurwitz numbers actually gives the moment cumulant relations in general, in complete generality of free probability. So this arrow is actually more general than all the other arrows. So that's why we think that this is a quite universal relation. So okay, let me start by presenting this universal relation. So the first thing that I have to present is what are monotone Hurwitz numbers. So we consider two non-negative integers and then two partitions of one of them. Then we say that double monotone Hurwitz numbers are actually counting number of possibly disconnected coverings of the sphere. You can see here the drawing. So this is the Riemann sphere. Here you have 0 and infinity. And you consider that the ramification profile over 0 is given by the partition lambda, and the ramification profile over infinity is given by the partition mu. And then in the middle, well, in above other points, we can have simple ramifications. And this number of simple ramifications is given by k. By simple ramification, I just mean that two sheets of the cover come together. And this is counted up to some automorphism factor that I'm not talking about. Okay, and there is another way of counting these Hurwitz numbers, actually. And the relation between these two ways of getting them is a very classical result and very beautiful. So we consider C lambda to be the conjugacy class of elements in the symmetric group on D elements of cycle type given by lambda, meaning just that the partition gives you the number of, so the lengths of the elements in this conjugacy class in the symmetric group. So the length of the cycles of the permutation. And then the double Hurwitz number. So for the moment, I'm not defining monotone yet. It's just giving you the number of tuples like this, in which the first one is of cycle type lambda, and then the other k are actually just transpositions, so meaning that they are of cycle type 2, 1, 1, 1, 1, 1. And then the product has to be of cycle type mu. And then we divide by 1 over the factorial, and this is exactly the same number as before. Okay, and then this definition helps us say very precisely what I mean by monotone, since this is an important concept of the talk. I want to explain it. So if we consider the transpositions to be written like this, so the first guy is the strictly smaller one with respect to the second one. Then the second ones, if they form an increasing sequence, weakly increasing, then the monotone Hurwitz numbers, we denote them like this with a smaller or equal here, and they are weakly monotone Hurwitz numbers. If instead they form a strictly increasing sequence, then the monotone Hurwitz numbers are strictly monotone Hurwitz numbers. Okay, and then we just package them in generating series. So the H bar just keeps track of the number of simple ramifications. So K is the number of simple ramifications, remember. And then here, this will be a polynomial in H bar, because strictly monotone is much more restrictive than weakly monotone. And this will just be a power series in H bar. And a very subtle but important remark is that here we are considering alternating signs. We already saw more or less why in other talks, but okay, this will just be giving us nicer formulas. Okay, so to consider the master relation, I have to define what I mean in general by topological partition function. So yeah, I was referring to some combinatorial problems, but actually here I just want to give this master relation in general. So I just want certain functions that package some numbers together. So how to do this? So we consider the Fock space, which is just the completion of the ring of symmetric polynomials with coefficients formal power series in H bar. So okay, these are the variables, P1, P2, P3, and so on. And then we consider guys indexed by Young diagrams or by partitions. They are just products of the PIs, where the I's are the parts of the partition. And then we consider this type of combinatorial factors that tell you something about the automorphisms of the partitions. Like this, we can define our topological partition function. So they're just guys on this ring that are actually of this form. They are exponential of something that has a topological expansion. So just meaning we sum over a certain genus, and we sum also over all possible partitions, so all possible Young diagrams. And then we have, this is a topological expansion, so we just have our H bar to the 2G minus 2. Here we put our numbers. Here, depending on how we package things, for example, here we have to divide by this factor, this automorphism factor, and we just put the piece here. But we can also write this series like this, and then this defines for us what we mean by Z lambda. So it's just the lambda part included in Z. And these guys will help us give the master relation. So actually we define the master relation between one topological partition function, actually these coefficients here, and another one that we will denote with a check, if these two problems are related by strictly monotone Hurwitz numbers like this. So this guy is equal to this automorphism factor, and then we sum over partitions of the same number of, which is partitioned by lambda. And then we put here strictly monotone Hurwitz numbers lambda mu, and here just the other problem. So we say that these two guys are related by the master relation. And then a completely equivalent way of writing this master relation is using weakly monotone Hurwitz numbers. And remember that this guy is alternating. So it has minus H bar to the K. Yeah, the fact that these two guys are equivalent is quite easy if you know the definitions of these, not just the definitions, but a bit more about these monotone Hurwitz numbers, but it's not difficult to prove. You can prove it, for example, using character formulas for these monotone problems. So this is an easy thing. So it's the two different ways of formulating this master relation. Okay, and then I want to finish by saying which other ways we have to package the same combinatorial information that we have in the topological partition function. And this allows me to already pose the open problem. What was the open problem in free probability that we managed to solve in this project? So yeah, giving the topological partition function is actually equivalent to giving multiplicative functions that are just functions from the poset of partition permutations to our ring, formal power series in H bar to our ring R, and with coefficients in our ring R. Okay, maybe you don't know what multiplicative is. I don't remember now if Jamie defined it this morning, but okay, but you already heard about partition permutations, and I will be telling you more about this later. And another equivalent way, which is a bit maybe easier to see the relation, equivalent way of packaging this information is just using correlators or endpoint functions. So it's just here we sum over all tuples like this, and we just put the same numbers that were encoded in our topological partition function. And here we just consider n variables like this. Okay. And then the open problem in free probability was actually what is the relation? So in free probability, there are some guys in here that are the moments. That's why I'm writing here moment cumulant relations. And these other guys, the check ones, will be the free cumulants. The problem in free probability was what is the relation between these two guys? What is the functional relation between these guys for n bigger or equal than, for n strictly bigger than 3? And why am I writing 0? Well, it's just because in free probability, these guys existed just for genus 0. And one of the things that we did with this work is defining all the concepts that you saw in Jamie's course, also for a higher genus. So they passed from first order to higher order. This gives you 0n, and we passed from 0n to gn. And it's more natural for us to just treat all the topologies at the same time because we are very used to topological recursion, to techniques coming from combinatorics. So for us, it's actually easier because it gives more structure to the problem to consider all topologies together. Okay, and this was known, of course, this relation was known for n equal to 1 and 2. You saw it in Jamie's talk. And it was also known, I mean, we proved it during my PhD thesis in the combinatorial setting for n equal to 1 and 2. And we also proved it for n equal to 3 in the topological recursion setting. So we actually know that this formula is general to any topological problem, topological recursion problem. So duality for n equal to 3. But we didn't know in the full generality of free probability because these things are not really included into each other. There are some non-empty intersections, but yeah, but we didn't know how to do for higher n, and this is what I will present today. So what is the strategy to find these functional relations? So we will actually start from our master relation that we first found in the context of combinatorics, matrix models, and then we decided, okay, let's try to see if what happens in general, if we just consider this relation in general. And we actually realized that this is actually equivalent to convolution, and this is a special convolution that I will define today because it will take into account also higher genus corrections with a zeta function. Zeta function that maybe you saw already in Jamie's talk, I think. Okay, but anyway, I can just tell you that these guys will be the moments and these guys will be the free cumulants, and actually this is just the definition of higher order free cumulants. And here this will also be the definition of higher genus, higher order free cumulants. Okay, so actually these two problems related with convoluting with zeta function is equivalent to these two problems that we can package in this other type of partition functions. being related by the master relation. And then we also prove that this relation, this master relation, can be translated, and it's actually equivalent to certain relations between the endpoint functions, the usual ones and the check ones, or the moment ones and the free cumulant ones, or the ordinary ones and the simple ones, depending on in which part of the relation you are. And this allowed us to prove the moment cumulant relations in the full generality of free probability, and also considering higher genus corrections. Okay, so now I want to talk a bit about the origins of the master relation. This part I will do a bit faster because I think most of you saw about this, so I don't want you to be too bored. But okay, but like this, we see also how it all started. And then, yeah, I will go back to free probability. So, okay, what do I mean by map? So a map of genus G is just a connected graph embedded into a closed oriented surface in such a way that the complement of the graph is a disjoint union of disks. And these disks, we call them faces. And we consider n boundaries, meaning that just n of the faces are distinguished in some way. So here, for example, we just distinguish two of the faces by saying, okay, we root one of the edges of the face in such a way that the special face is sitting on the left of the root. And the same thing here. And this is then a map of topology 1, 2, because it's drawn on a surface of genus 1 and it has these two distinguished faces. Here we consider just graphs embedded on certain surfaces, here genus 1 and here genus 0. You have to imagine this is on the sphere. But these gray faces are not of the topology of the disk. So they are not maps. So they are not allowed, but we can add some edges and then they are perfectly fine maps. So yeah, this is topology 0, 1 and this is topology 1, 0, because there are no marked faces. And then, okay, these are the classical maps. This is a very, I mean, there is a very active field of research just on the combinatorics of these objects. But now I want to talk about the special ones that we defined because they will be related to free cumulants. So yeah, what do I mean by simple map? So I mean just that the boundaries are simple polygons. So here in these drawings, the boundaries are the green and the red. As you can see, there are these arrows. So by simple, I mean that when I go around the boundary, so around the edges of the boundary, I want to enter once every vertex and exit once. And that's it. So this one is okay, is simple, but this one is not, because here I enter once, I go out, and then I enter again, and then I go out. So this is not simple. And this is not simple, this is simple, but it's not fully simple because fully simple needs to have disjoint boundaries. So, okay, this one is not simple, this one is simple, but not fully simple, and this one is fully simple because the boundaries are not touching each other. Okay, then, sorry, are there questions? I don't know how easy it is actually to hear questions, because when I was listening to talks, I was not hearing anything.
Be fully simple, they can't even touch at a vertex. Is that what you said?
Exactly. So
Okay,
these ones
thanks.
are touching at a vertex and they are not fully simple. Yes. Okay. Yeah. Then I want to also package these numbers of maps, ordinary maps and fully simple maps into generating series. So here I just consider generating series of ordinary maps of genus G and n boundaries of lengths L1, Ln, just the sum over such maps of, so the weight per such a map is just a product of TKs where K is the length of every internal face of the map. So, okay, in the map, so the map is just a graph embedded on the surface. So it has faces, no, as we said. And then some faces are special, and these are the boundaries. So these are the external faces. The rest of the faces, so in the drawings, the blue ones, they are internal faces. And every triangle, for example, carries a T3. So if you have a T3 to the 5, this means that there are 5 triangles in your map. Okay, so and then this generating series, the coefficients will just count certain maps with a number of given triangles, pentagons, quadrangles, and so on. So you encode everything in such a generating series. And you do exactly the same for fully simple maps. And then it's a classical result that the generating series of ordinary maps is related to certain correlators on the hermitian matrix model. I will tell you precisely how they are related. And then we found the counterpart result, so the relation to certain correlators of fully simple maps. So we consider the ensemble of hermitian matrices, n times n hermitian matrices. We consider such a potential. So here you have the TKs that keep track of the internal phases of length k. And then you consider the unitary invariant measure on the hermitian matrices. So it's just a Gaussian ensemble, but here you have these T's that deform the Gaussian potential. And then you know that these moments with this measure will be related to the generating series of maps, and the classical cumulants of powers of, so traces of powers of the matrix will be related to maps, but connected ones. So, okay, the moments are related to disconnected objects, and the cumulants, classical cumulants, are related to connected objects. And then I have to define what are the expressions that we need to put here to just capture fully simple maps. Then if you know about this relation, you will understand why. If not, well, okay, maybe you will need to think about it, because yeah, for this you need to know a bit about the combinatorics of Wick's theorem. So, okay, how do we define the fully simple correlators? Here we just consider cycles in the symmetric group on n elements. And then we just consider products of matrices along this cycle. So these guys will actually be certain guys that also appear in a trace, because we have like Mij, Mjk, Mkl, like this. So they are elements that typically appear in a trace. But since it's along a cycle, this prevents guys from the cycle, because of course this is what we mean by cycles. It prevents guys from the same cycle, from the cycle to be the same. So these guys will all be different, and this actually imposes that the faces of the map will be simple. So the boundaries of the map will be simple. They will not have self-intersections. And then if we take n disjoint cycles, so the cycles also have like disjoint guys, then this will prevent the boundaries from touching each other. So it will make that the map is fully simple. So, okay, these guys will be related to fully simple maps, disconnected, and these two connected fully simple maps. And like this, we establish the first relation to free probability. So, okay, this is from old works of mine with Gaëtan Boron. So you can define certain moments just by these limits of, so you have to multiply by n to the power n minus 2, take the limit when n goes to infinity of the cumulants, and this gives you certain moments. And then you can also define free cumulants using classical cumulants of these expressions. This is not in the original way in which people considered certain free cumulants from matrix models, but we proved that it's equal to this. To these expressions with these p's that we defined to match fully simple maps. Okay, and then the relation to maps. Okay, so this is a classical result already from the 78 from this physicist, that cumulants of traces of powers of matrices, it's a generating series of maps in which you package all topologies together by powers of n. So the size of the matrices. And we prove with Gaëtan that if you take classical cumulants of these expressions, you get fully simple maps. And the way to prove it is as I indicated while I was explaining these expressions. So remark, for more general multitracial Hermitian matrices, you can also give the relation to certain maps, but these will be stuffed maps in the sense that the faces don't have topology of the disk, they have higher topologies, but okay. This will not be very important for the talk. So you can go from maps to free probability, actually. For these measures, you can define your moments just from generating series of planar maps, so genus 0, and free cumulants from generating series of fully simple maps. And of course, for us, it's very natural to consider here higher genus, also from the topological recursion point of view. So this gives us already a hint that there should be a notion of higher genus moments and higher genus free cumulants. But it was not clear until very recently if these guys were going to be meaningful or not. If the notion that you can invent of GN freeness out of these guys has the nice properties, the type of properties that Jamie was explaining in his mini course. And it turns out that it does have all the nice properties. So it's a natural notion that can be useful to just control all the corrections of, for example, random matrices ensembles. Okay, so a little bit more on the origins of this master relation. So what was the first instance in which we found this relation? It was actually relating fully simple maps, disconnected fully simple maps to disconnected, so these big dots means disconnected, to disconnected maps through weakly monotone Hurwitz numbers. And the first way we found this result is using matrix models. So we actually found a kind of fully simple correlators. It's actually more general than that. So because here you can put any unitary invariant measure, and this proof works perfectly. And the measure is unitary invariant. So these expressions are not unitary invariant. The traces are, but these expressions are not. But the measure is unitary invariant. So the first thing that we can do is we can average over the unitary group. And then we can use Weingarten calculus to express these guys in terms of these guys, because these guys, we know that they are the building blocks of unitary invariant things. So this makes a lot of sense. The surprising thing for us was that we found very nice coefficients that are given by these weakly monotone Hurwitz numbers. And then once we had this relation, as I said before, it's easy to find this relation. They are equivalent, and this is just a small manipulation that relates this to enumerative problems. And then once we found this relation, we were quite happy because these guys don't have signs. So remember here, there were alternating signs that they are hidden in the definition of the generating series, but here everything is positive. So this kind of told us that there should be a combinatorial interpretation of this formula. And this is how we found the two combinatorial proofs for this formula. Actually, we found two independent proofs. One was Gaetan with Severin, and the other one was me with Normandon. This is this work over here. And then I was talking to Gaetan, and we said to each other, actually, we also have a proof. Maybe it's the same. Let's talk about it. And actually, they were different proofs that have a nice relation. So I will be presenting the one that is easier to visualize. It's using bijective combinatorics. And actually, this proof gives us an idea of what this master relation means in general in combinatorics. And I will be presenting what it means for constellations in the end of the talk, if I have some time. So, okay. To find this bijective proof, the first thing that you have to realize is that strictly monotone Hurwitz numbers are related to the number of the Descendant-Enfant. So what do I mean by Descendant-Enfant? I just mean maps in which each edge is adjacent to a boundary and to an internal phase. Here the boundaries are considered blue and the internal phases are considered red. So they are bicolored maps. They have phases of two colors, and only red phases can touch blue phases in this Descendant-Enfant. Then it turns out, and this is you can prove it in many different ways, but there is a very elementary proof of this using just ways of encoding Descendant-Enfant in 3 permutations, and here the definition using well, the characterization using the symmetric group that I showed before. So these two guys are counting the same. And then like this, you can already have the idea of the proof. So to every map, you can associate a fully simple map. So you can just start from a map. You can simplify the faces or fully simplify the faces. Then you will lose some information because, of course, with this, how do you know how to recover this guy? But you keep the information of the internal faces. And then with the descent enfant, you keep the information of how the boundaries were glued together. And this is the idea of the proof. Then you have to check many details, but this is the idea. Here you have an instance of this master relation, but that is a bit more intricate. So you start from an ordinary map that looks more complicated. It has a very complicated boundary that touches a lot itself. And when you simplify it, you find all these guys. So you find something that is disconnected. Yeah, and then the descent enfant tells you how to glue the fully simple pieces together, and the fully simple pieces tell you what was the internal structure of the ordinary map. So this is the slogan of the proof.
I have a question.
Yeah.
Can you realize this descent fonts by the two matrix models where all the TIs are 0?
Yes, exactly.
And do you use that, the result or the spectral curve of the two matrix model in this proof, or do you use this fact?
Not at all, no. Actually,
Okay.
this proof and this result has nothing to do with topological recursion.
Okay.
It was actually, I mean, we were trying to find the topological recursion for fully simple maps. We already had it for, it's already a classical thing in topological recursion for maps. And we were expecting that for fully simple maps, you would have the one for the exchanged curve, just because of hints coming from free probability and also because of the lower topologies counts that we were finding. But we still didn't know how to prove the topological recursion here. We were just finding relations between these problems to see if this could help us find the topological recursion. And it was actually using these relations that then the Russian team like Bitskov, Dunin-Barkovsky, Kazari, and Shadrin found the proof using this relation. But it was not easy. Like they had to use going to the Fock space, all the relations that they know in the Fock space. So, okay. Yeah, so we don't use the two matrix model at all. But this is good to keep in mind. Okay, and then, yeah, the other big motivation for us is, can we say something about the symplectic invariance in topological recursion? So you start from a topological recursion problem, you get your omega gns, you get your numbers for n equal to 0, you apply a symplectic transformation to the spectral curve, you apply topological recursion, you get some numbers, and symplectic invariance tells you that in principle, there is a relation between these guys. And I put as question mark because there is a relation up to corrections that still need to be understood. So what we know now is that if you put here maps, so at the level of combinatorics, it's very clear that closed maps, closed ordinary maps are equal to closed fully simple maps because the fully simple condition is on the boundaries. So this made a lot of sense in combinatorics. When you compute the FGs from topological recursion, you don't get an equality. You get something with corrections, and these corrections have a meaning, and it's more and more clear for us, but it's still not completely understood. So what we know is that if you run topological recursion with this spectral curve, okay, here you have complicated generating series that contain the T's that keep track of the internal phases. On the other side, when you exchange X and Y and you keep the same omega 02, you run the topological recursion, you find generating series of fully simple maps. And again, our proof doesn't use the master relation. Our proof is combinatorial, is using these complicated maps called ciliated maps that we were studying for a completely different problem. And the proof of the other team was using our master relation. Okay, but I will not say more about this. Let me just go to surfaced free probability. So luckily, Jamie already introduced partition permutation, so I can go a bit fast and hopefully you will be able to understand the idea. So, okay, partition permutations were introduced to just introduce higher order free probability, so higher order probability spaces and higher order freeness. So, okay, it consists of a partition, of a set partition, of D elements, and of a permutation. So these are just, this is the notation for partition permutations. And the condition for this to be a partition permutation is that the partition has to be, so let me say, the permutation has to be finer than the partition. What does this mean? So let me just give an example. So if we have here a partition of 9 elements, so we just have these 2 blocks of the partition. Here we have a permutation. So it satisfies this condition because these 2, so if we forget the cycle structure of the cycles, this is what I mean by this 0 and gamma. We saw the same notation in Jamie's course. Then it just means that the blocks of this associated partition are included in some block in U. And these 2 blocks are included in here, so they satisfy this condition. Then we define the length that was also defined by Jamie like this. It's always non-negative. And for this specific case, this is the finest guy. So it just, all elements are fixed. And this is also the finest partition. So it's just all singletons. For this particular case, you get a 0 for the length. Okay, and then we also consider a product on partition permutations.
I have again one question, sorry. So in U, you go from 1 to 9, and in gamma, you go from 1 to 8. So this is allowed that they have different length?
Sorry, yeah, this just means that I forgot to put 9 because it's just fixed. So
Okay.
you can consider that is a parenthesis 9 here. And then the cycle 6, 7, 8, and the cycle 9 alone are included in this block. So no, it's not allowed that they have different lengths. They should have the same length. And you should think of this permutation inside the symmetric group on 9 elements, not on 8 elements. Okay, yeah, thanks for the question. Maybe that was confusing. So what do I mean by the product? So I just take the join of the 2 partitions. So this is just the smallest partition that contains these 2 partitions, contains in this sense over here that the blocks have to be contained in the blocks of the bigger one. And then for the permutations, you just take the product. And then what they considered in this paper of 2006, where they introduced a higher order free probability, so Collins, Mingo, Speicher, they considered that this was going to be 0 if this condition was not satisfied. And this condition is actually a condition of planarity. And what we do to be able to include all our genus corrections is just we remove this condition. So we have different ways of dealing with this, and some are more suitable for some things and some are more suitable for other things. But since I'm short on time, I will present the easiest one, which is just remove this 0, remove this planarity condition, and consider the higher genus corrections taken care of by some H bars. So this you will see in the next slides. This is just a little spoiler. So, okay, we consider convolutions of functions on partition permutations. Just like this, I think you also saw this in Jamie's talk. We consider the special delta function that is just 1 if this is really the trivial guys. Otherwise, it's 0. So this is really the unity. This we want it to be the unit of the convolution, if we think of the convolution of a product. And then the zeta function is just 1 if this guy is equal exactly to forgetting the cycle structure of the permutation alpha. Okay, so if this is the case, if you have here an equality, the zeta function is equal to 1, otherwise is equal to 0. And then you can show that there exists a unique mu function, which is characterized by this. It's characterized by the fact that mu convoluted with zeta is equal to delta or the other way around. And this can follow also from the general theory of Rota. You saw this in Mingo's mini course yesterday, I think, for n equal to 1. But actually for higher n, this doesn't work because you can put a poset structure. I mean, for this to be true in general, you need a poset structure on your partition permutations. And the poset structure that you can put doesn't give this zeta function. It gives another one. So, okay, there is a bit of mismatch. We keep calling it the poset of partition permutations, but it's not the poset that gives you the natural zeta function that is like, comes from the general papers of Rota. So this is important to keep in mind if you care about these things. Okay, so here I re-represent the open problem that we heard many times, so maybe I can be a bit fast. So we consider multiplicative function. It just means that these guys will just depend on the conjugacy class of gamma. These guys are just products of these guys, in which here we just put the partitions that are just the biggest partitions. So it's just the partition that has just one block. And then we consider that these are the building guys. We just define them like this. So we just call them F, L1, Ln. Then we consider certain moments on a higher order probability space and certain free cumulants defined just like this. And also you saw this also in Mingo's mini course, and you will see it better tomorrow, I guess. Then you can encode the moments and free cumulants into generating series. So I will call generating series of moments with M and generating series of free cumulants with C. And my free cumulants are called kappa. And here we have the higher order ones. And the question in free probability was, what is the functional relation, as I presented before. So this was known for n equal to 1 by Voiculescu, combinatorially proved by Speicher using non-crossing partitions. This we saw a very nice explanation in Jamie's course. We also saw this formula, which is the moment cumulant formula for n equal to 2. But then these proofs using the definition of partition permutation seemed hopeless to generalize to higher n. Then we tried from the combinatorics of fully simple maps. We managed for n equal to 1 and 2 in the full generality of free probability. But for n equal to 3, we could only prove it from the topological recursion problems. And for higher n, it was also not clear to us how to prove it. And okay, yeah, I will present briefly how we managed to solve the problem here. So yeah, let me continue so I can give the last ideas. So here we consider a higher order probability space. This we also saw in Jamie's talk, so I can do it a bit fast. So we have an algebra, we have a collection of moments. There are certain functions with conditions that we saw precisely in his mini course. And we decorate partition permutations with the elements of the algebra. And then we can consider moments that are now multiplicative functions just by using the moments of our higher order probability space. So they are just guys like this. They are just guys from partition permutations. So and we defined what they are for these guys, and then they are multiplicative. So we can extend it to any partition permutation. And then they are decorated by these guys. And then here we use the moments and these products to define these guys. And then the free cumulants are just defined by convolution with zeta, or equivalently by summing over certain non-crossing partition permutations. This I will not enter into details, but you also saw in Jamie's talk and a bit in Octavio's talk. And equivalently with the mu function. Then we have a notion of higher order freeness, which is just defined by vanishing of mixed cumulants. This you saw also very nicely in Jamie's talk. Then you also saw that higher order cumulants linearize, adding higher free variables. So higher order free variables. In the same way that classical cumulants linearize, adding independent variables. Okay, this you saw also in Jamie's talk, so let me go fast. And then let me say a few words about how we extend this to higher genus corrections. So as I said before, we just extend multiplication on partition permutations, just like this. We call it dot with a circle, and it's just as before, but we don't take 0 with the planarity condition, we just consider everything. And this can also be understood as multiplication on certain surface permutations that I will not introduce because it's equivalent to this. But let me give an example so you have an idea of how this genus appears. So you have here a permutation. You can represent it by this polygon. And the partition is just exactly forgetting the cycle structure of these guys. So that's why I didn't write it down, because it's just the one that is equal to the partition associated to this permutation. And here exactly the same. So we just consider this permutation and the partition that is exactly the same as this permutation, forgetting the cycle structure. Then we take the product and we consider that we built this guy because the permutation looks like this, and well, this makes sense. And then the partition will be exactly the same. And here you have that the planarity condition, you can check with this formula, is satisfied. So you have that this length is equal to the sum of these lengths. But what happens if we violate this condition? Well, for example, here we consider just the partition that takes these two blocks together. And then this will not be equal to this. This will be 6 and this will be 4. And this mismatch, we can take into account about these mismatches exactly by introducing some genus in these partition permutations. And this brings us to the notion of surface permutations that was kind of already hinted in the appendix of Collins, Mingus, Niadi, Spiker. Okay, and then the idea is that with this extended product, we can extend the multiplication, we can extend the convolution, we can extend the zeta function. We just add h bar, so a grading by h bar that takes into account what is the length and what are these mismatches. And we can prove that there exists an extended Möbius function that is uniquely determined by this as before. And with all these extensions, we can define a notion of GN freeness. And we can prove the extension of Voiculescu's result that tells you that freeness appears very naturally in random matrix ensembles. So if you have two ensembles of random matrices of size n, one of them is unitary invariant, but they are independent from each other. If they have, if they admit, if their distributions admit certain limits up to a certain order G0 and 0, then the limits are free of order G0 and 0. Okay, here I'm not giving the details, but this allows you to control all the corrections of, well, all the higher order corrections just beyond the leading order. Okay, and then let me briefly present how the moment cumulant relations look for us, but you saw similar relations in Alexander's talk. And then, yeah, then I will finish with the idea of these constellations.
So the definition, sorry to interrupt.
Yeah.
The definition of freeness is vanishing of cumulants, right?
Exactly.
Okay, thank you.
Yeah, and then we consider we consider a partial order in these couples Gn. And then Gn freeness means that all smaller Gn's have to be 0. So the vanishing of the cumulants of a topology smaller than Gn have to be 0. This is the definition. Yeah, and then, okay, let me present briefly these moment cumulant relations. So we consider a bicolored trees. So they have vertices that are white. They are labeled from 1 to n, and they have certain valencies. And we have also black vertices that cannot be univalent. Okay. Then we also consider certain weights that are differential operators that you will see precisely in an example that correspond to the white vertices. And they are certain operators that act on guys that involve the first order cumulants. This is what maybe you can remember. And then for each black vertex, we denote like this, like I of the tree, because I will present the relation only for genus 0, so there will only be trees, because otherwise it's a bit too technical. But we actually prove the moment-free cumulant relation for any topology. And yeah, then these guys are just the subset of white vertices connected to this black vertex. And then you're already ready to see the relation. So moments of order n of genus 0 are related to cumulant guys with this formula. So there is a sum over r's, a sum over trees with certain valencies that have to do with these r's, a product of these differential operators that you will see now, and then a product of these cumulants. So let me summarize. The weight per tree is just the product of these cumulants, and this prime just tells you that the second order free cumulants should be replaced with these guys. So there are these corrections when I is different from j. This is a bit subtle because you may complain, what does this actually mean? Do you have to expand this or not? Believe me, this is well defined, but it's not so trivial to see. So, okay, just I want to give a quick example. So for n equal to 7, this is a possible graph that you can get. This type of guys we don't want. And then for a vertex that is 4-valent, you just will associate a cumulant of order 4 with these 4 variables that have to do with the labels of these guys. And then the weight of the tree will just look like this. We will just take the product over all weights associated to every black vertex. Okay, so I just want to, here I'm just commenting that there are actually a finite number of guys on the sum. Okay, this is not difficult to show, but maybe let me go a bit faster because otherwise I'm running out of time. And then for n equal to 3, the trees that you see appearing are just these 4 trees. Then the operators, the differential operators, I promised that I would show them. They look like this. Okay, they look infinite, but they are not. Because only the guys with m smaller or equal than r will give contributions here to this sum because of just this taking this mth coefficient of these guys. And then this tells us that there are only finitely many terms on here. So you can express moments in terms of combinations of cumulants. And then I just want to show how the formula looks for the case n equal to 3. So here I did all the details. So for this first tree, you have just this guy. For this other type of trees, you have this type of guys. And then for r equal to 0 and 1, which are the only possibilities that appear in these guys, you just have these guys over here. It's very easy to compute from this formula. And the moment cumulant formula for n equal to 3 and genus 0 just looks like this. This is quite explicit, and this is the formula that you can find in general for any topological regression problem. But here we proved it from the master relation. So we proved it for a much more general thing than just topological regression, because the master relation is more general, if you want, or at least, well, yeah, it's not clear if one problem is included in the other, but it's clear that this is more general because it's for any free probability problem, let's say. Okay, and then, well, to prove these planar relations, what we actually do is we prove them for all the other topologies, and then we specialize to genus equal to 0 to solve the open problem in free probability. The idea of the proof is what I explained before. And this gives for us a nice theory of higher order freeness that behaves nicely, as I said before already. This here, I wanted to give an idea of this step number 2, but let me skip it and go to this idea of constellations that should be new to everyone. So a constellation is just a map. So M constellation is a map in which there are faces colored in black. So the black ones here are the ones that contain numbers. And then there are white faces. So they are the other ones here. And yeah, it has to satisfy that every edge is adjacent to a black one and to a white one. And then the black ones are of degree m. So this is the m of the constellation, and they are the hyper edges. So you should imagine that the guys with the numbers are like the edges. And the white faces are actually of degree a multiple of m. And then there is also another condition, that there exists a coloring of the vertices such that around every black face, the vertices are of color 1 to m clockwise. Here the colors are not numbers, the colors are colors like purple, red, green, purple, red, green. Okay, so this needs to be satisfied for this to be a constellation. And these guys, you can encode them with m+1 permutations, acting on hyper edges in such a way that the sigma i's from 1 to m, they tell you the hyper edges around the vertex of color I, and the sigma 0 tells you what are the faces of the constellation. Okay, and here I gave the example, so you can see that this is true. For example, for purple, this is 1, 3, and this tells you that around this there is 1 and 3. Then there is 2 alone, and then there is 4, and then there is 5, 6. Okay, so you can encode the constellation like this with these 4 permutations. And then this allows us to show that actually another instance of the master relation is a tower of constellations. And this actually has a very nice interpretation in free probability that is very related to the end of Octavio's talk. And it was them who told us that they knew this interpretation in free probability. And they were asking what could be the interpretation in topological recursion. And well, we realized that you can prove the master relation for constellations. You can prove the tower just combinatorially, as I show here, but maybe let me skip the details. Let me just say the idea. You start from an m+1 constellation, and then you simplify it. So you just take the last color, let's say the last color is red, and then you open it. And then you get the simple m+1 constellation that looks like this. And then you realize that since you have opened the red color is useless. So you can forget about the red color, and this will be an M constellation. But if you forget about how the red was glued, you need something that tells you how to glue it. And this is what the descent does. The descent tells you how to glue the red, and the descent doesn't know about the rest of the colors. So this is how the bijection works. Now we know all the details of this, but we still wonder what is the relation to the work of Octavio Arizmendi, Felix Light, and Speicher, who were very nice to explain us what it meant for them to convolute with zeta. So for them, they just take a circular element, which is free with respect to another arbitrary element A. And yeah, their interpretation of passing from a moment to cumulants is just conjugating with respect to this circular element. So a natural question that I actually realized is very, very natural preparing the talk is the phenomenon that they proved actually true for higher genus moments and free cumulants that we defined in our work? So I think this would be a nice question to investigate. And I'm sorry I'm not there to discuss with Octavio. And then, yeah, I have to mention, because it's also quite important, that we conjecturally think that if you have topological recursion on one side of the master relation, you will have topological recursion on the other side, in which you apply a symplectic transformation of the spectral curve. And it's very remarkable that the formulas that Alexander presented are actually the same that we find for genus 0. I mean, so he uses genus 0 and a loop insertion operator that is not even clear to us how to make sense of this loop insertion operator for the fully simple problem, for example. But he applies it and he finds the same relations. So it seems that these relations are quite universal. At least they are shared somehow between this master relation in this symplectic invariance of topological recursion. Yeah, so, okay. We wonder also how this extends to the orthogonal and real realm and other things, but let me finish here. Sorry to go over time. Thank you for your attention.
Hey, thank you. So any further questions, comments? Yes.
Hi, Elba. It's Jamie Mingo here.
Hi.
So I had a question. So about any examples where you can write out explicitly the M's or the C's, for example, like a Marchenko-Pasteur or semicircle law. So I mean, did you ever check that? Because there are some formulas already in the literature about these moment generating functions for these higher order moments. And did you ever check to see what your formulas give compared to those formulas?
No. So we know, for example, that for the most trivial case for GUE, so for Gaussian ensemble, so without internal phases, so you don't have the T corrections. In that case, the fully simple maps, let's say, they are trivial. So you get a formula between moments that are non-trivial and things that are almost all trivial. And the formulas that you get are exactly Harris-Aguirre. So for example, for that case, we know that that is what you get. But it's very interesting for us if you tell us like which are the examples, the nice examples to look at and to compare to our moment cumulant formulas, because yeah, I don't know so much about that. So so you said Marchenko-Pasteur.
Yeah, well, I mean, those are ones where, at least to the second order level, there's formulas in the literature. Bai and Silverstein in their book have something.
Okay.
Yeah,
So
okay, another question I had was about the case when the black vertex has degree 2 is more complicated when the black vertex has degree 3.
Yes.
Can you explain that?
So this is quite annoying, intriguing, but it's a very typical feature in topological recursion that the 0-2 guys are not exactly your combinatorial problem or enumerative problem. They always carry these corrections that are important for running the topological recursion. Yeah, I don't have a deeper reason why. I mean, these guys are important for the moment cumulant formulas, and they are quite annoying, to be honest.
So it sounds like, I mean, you have to add more terms, right? That's the W6 times W3 over the square of the difference.
Yeah, exactly.
It's adding some more terms, and I'm curious to see when you use your formulation why. I mean, well, of course, we had a thing with the difference in the bottom too, came from the second different partial of a log of a difference quotient. Okay, no, I just wondered if there was a topological reason for it.
So for example, for the formula for 0-3, that is, I give it very explicit here. These guys are there and they are very important. And if you try to prove this formula either by combinatorics of partition permutations or by maps, you see more or less the meaning of all the terms. But these type of guys make it very difficult to have the patience to finish the computations to give the combinatorial proof. Because what they do combinatorially is that they combine certain boundaries with other boundaries. And then you also have signs and things that get subtracted and get combined together in a complicated way. So it's quite non-trivial what happens there.
Thank you. Because I was thinking of doing the case of 2 circles tomorrow, but that's the one that you said is most difficult. But it may be when there's only 2 circles, it's not so bad.
No, when there's 2 circles, it's not so bad, I think.
It's when the other circles.
If you want, it's a bit pathological because it's still special. So if you look at the proof with maps, you have this cyclic symmetry that will not appear there for 0-3, for example. But it's for 0-2 is definitely doable. For 0-3, I already never had the patience to finish the computations because I could only be sure that, okay, this combinatorial proof should work when we had proved it already in some other way, and then I never had the patience to finish the computation.
Okay.
But I will still like to understand better what is the correspondence. I mean, for example, if we expand these formulas in coefficients, so if you just get equalities of numbers out of them, You can also get equalities of coefficients out of your formulas. There doesn't seem to be a one-to-one correspondence of the terms, and that I don't understand. So yeah, these things we need to explore better.
Yeah, I have also a question. From the point of view of maps, you can also have a combinatorial problem which has n fully simple maps and m ordinary maps, ordinary boundaries and n fully simple boundaries, I mean. And would you also be interested in looking at this kind of stuff, how this is related, or which kind of functional relation you have there to just ordinary maps?
So we thought of doing this because it seems a natural thing to do, and also because probably the relations should be, I mean, if we have a hope that our relations are really related, they are the same and they are different instances of a more universal thing, I guess this should all coincide with the relations between these mixed correlators coming from two matrix model. But we didn't do it from the point of view of maps or from the point of view of our master relation. For example, our master relation is not, I mean, one could try to invent the master relation for the mixed guys, but we didn't do it because we didn't really find the motivation to do this. But in your work, you find relations for these mixed guys. So it would be nice to see if, I don't know, for some reason, those guys have an easier combinatorial interpretation or something. So for example, we looked a bit at the cancellations that you get for genus zero formulas. And we thought, okay, these cancellations will also apply for higher genus. But when you apply this cancellation for higher genus, for example, you get things that look a bit less fundamental to us, because at least now, so the formulas are still very ugly and scary, but now we worked a lot with them. We know the meaning of the terms in this Fock formalism of the operators. And if you apply the corrections, these guys don't really have a meaning in the Fock space so far. So maybe they will at some point. So it's not very clear, like, what is the right approach to try to get these formulas for higher genus in the context of topological recursion.
Yeah, for me also interesting is how you get the higher genus cases, because you had this sign of z over z, this weird function where you have all this higher genus contribution, and also this operator O is very complicated for higher genus.
Yeah.
I mean, how that I mean, I'm just curious how that is constructed, but okay.
How that appears, I mean, it's of course it's almost impossible for me to tell you the details now, but I can tell you the idea that maybe you already know. But the idea is that you start from the master relation, the one that we found from combinatorics, using the monotone Hurwitz numbers as like the transition from one problem to the other. And then you can express that relation in the Fox formalism. This maybe I saw something. I said something in this slide. Where is it? Here. Yes, here. So this master relation, you can express it in the Fock formalism using certain operators that have to do with strictly monotone Hurwitz numbers. You can express this express them in several different ways. And then these guys are really very good with identities of operators in the Fock space. And they proved these very complicated formulas for this conjugation by these type of operators. Then we use those formulas that now mean something to me, but I don't know if I can say much more, because it's a lot of algebraic manipulations. And when I was really trying to prove the moment cumulant relations combinatorially, our collaborators coming from the Fock space world was saying like, no way, no way they're gonna do this. This is completely crazy algebraic manipulations that mean something in the Fock space, but combinatorially, I don't know. Yeah, and how to prove this for the generality of topological recursion, I also don't know. I guess one possibility would be to try really to go through the proof of Henao-Antin for the two matrix model and prove that in the end the formulas are the same, because I think their formulas can also be generalized to these mixed correlators, and then you can try to compare, but it looks very complicated. Also because there are certain problems of definitions, like for example with the loop insertion operator, you had these problems of how to define them. On one side for the two matrix model is the same, like how to define these mixed guys in the full generality of topological recursion is not clear.
Okay, we have two more questions, very quick ones maybe.
So sorry, just one comment. I mean, so because you mentioned the sun, I mean, we know that absolute Galois group acts on the sun. So, and this descent d'enfant is part of your data. I mean, it might be interesting to look at how this enters into this game also. I mean, because it looks like part of the things now is moved by absolute Galois group. So it might be brought into the picture as somehow, yeah.
Yes, it's a very nice question. I have no idea, but I would really like to look at that. Like, yeah, I don't know if it may have something to do, but some people working on algebraic geometry or operats, this type of things, said that the relations for 0, 1 and 0, 2 look like something very fundamental to them. And then their master relation is something much more general. So I don't know, it would be nice to understand what happens in algebraic geometric problems, in operatic terms, and also in with respect to the action of the absolute Galois group. Yeah, absolutely, it's a very good question. I don't know if you have a hint or where to start. I would be happy to hear.
Thank you.
Also, okay, one more question here. Last one.
Hi, Elba, this is Octavio. So is your theory containing infinitesimal freeness? So the case genus 1 and order 0, this coincides with infinitesimal freeness?
It coincides if we allow, this I completely put under the carpet in the talk, but if we allow the powers of each bar to be just integers, not just having 2G corrections, but also having some genus that is 1
like
over
a
2.
half.
Like a half, exactly. Then we recover, so what we call 0, 1/2 freeness is exactly infinitesimal freeness. At least one of them that we found in the literature, that was the one that you were pointing to us. Then we discovered that there are many other things, and I'm not very sure how they relate to each other, like B type or this type of things. I don't know how they are related, and I don't know if they are all included, but infinitesimal freeness, the one that you told us about, is just exactly 0, 1/2 freeness.
Okay, thank you very much. Very nice.
You're welcome.
Okay, okay, there might be more questions, but we have to cut it here because we have already gone 20 minutes over time. And thank you. Well, this was the whole idea, having these questions and all things. Thank you again, and yeah.
Yeah, feel free to write to me or whatever if you want to discuss more.
So we have a breaks, and we will shift the other talk another 15 minutes. So we'll start at 3:45. The next talk. Okay. Thank you all. Bye. Thanks.
Bye-bye.
Bye.
Bye.